Okay, so we talked about buffers, and we're going to move on and talk about other types of aqueous solutions. So first one to talk about is solubility product constants. And if you remember all the way back in the first semester, talk about things that are soluble and not soluble, or insoluble, I should say, and what they mean. But the truth of the matter is, things that are not soluble, they do dissolve a little bit. So an example is fluoride here, calcium fluoride. Calcium fluoride solid is in equilibrium with calcium ions and two fluoride anions. And then we have the solubility product constant. So, so products, calcium fluoride squared. So calcium single power fluoride squared over the concentration of calcium fluoride. Concentration of a solid is constant. Therefore, the KSP, the equilibrium constant solubility product, so solubility product constant, is equal to the ions just raised to their powers. So calcium times fluoride is squared. So that's applying equilibrium constants to other things. So let's do this. Calculate the molar solubility of lead chloride in pure water. And also given the KSP, solubility product constant, is 1.7 times 10 to the minus 5. So the KSP, of course, writing lead chloride, it's going to dissolve into lead plus 2 ions and 2 chloride ions. And and the KSP then is the ions right there is lead plus 2 chloride squared. The way you solve this problem is you do equilibrium. So you have initially you have no lead and no chloride, and the change, I use a dollar sign. The book uses an S, but my S looks like a 5. So I say plus solubility plus 2 solubility. So this is the shift right. In this case, there's the equilibrium is then solubility to solubilities. And the KSP is equal to the lead plus 2 plus chloride, or times chloride squared, or I can put in the numbers 1.17 times 10 to the minus 5 equals solubility times 2 solubility squared equals 4 solubility cubed. So that means the solubility is going to be 1.17 times 10 to the minus 5 divided by 4, the cubed root of that. And so what is that? I'm going through the buffer, titration curve, I guess where is solubility product? Okay. And it is 1.43 times 10 to the minus 2 molar. So that means that for uh, lead chloride, which is insoluble, but it will dissolve at 1.43 times 10 to the minus 2 molar. So not that much. So it's 14 millimolar. So it certainly is not going to dissolve a large amount there for lead chloride. So why don't you, or here's another one. Look at this. We're given the molar solubility, calculate the KSP. So same idea, silver sulfate, and you should know how to write these out. This would be considered chemistry common sense. Silver sulfate will dissociate into 2 silver ions and 1 sulfate ion. So initially 0, 0, the change is 2, 2S, and the solubility there, equilibrium, this is plus 2S plus S. 2S and S, so our KSP is going to be the concentration of silver ion squared SO4 minus 2, which is equal to 2 sulfur, solubility squared, solubility equals 4 solubility cubed, equals 4 times 1.2 times 10 to the minus 5 cubed. So you can see it's a really small number. So really small number. Huh. Look in the book, it says this should be minus 2. There's a mistake in this one. Okay. So let's put this was minus 2. So 1 point, I guess this was updated, 1.4 times 10 to the minus 2. So putting that in your calculator, you get 1.1 times 10 to the minus 5. Okay, there we go. Huh. I did not realize there was a mistake there. Sorry about that, folks. Okay, so this is a similar problem as the other one, but you're just kind of switching it around, the number there. Okay, so calculate molar solubility in the presence of a common ion. So we talked a little bit about before about this with acids. So what is the molar solubility of a calcium fluoride solution containing 0.1 molar sodium fluoride? So the difference is now that initially we have 0 calcium, but we have 0.1 molar fluoride. So the initial change equilibrium, because calcium fluoride and sodium fluoride have a common ion, that's the fluoride. So the change then, we have a 0 here, so we still shift right. So we're going to have plus solubility plus 2 solubility there. Equilibrium is solubility, and 0.1 plus 2 solubility. So our KSP are just the ions, so it's calcium plus 2 fluoride squared, which equals solubility times 1 plus 2 solubility squared. And the KSP, I'll just go ahead and put the number 1.46 times 10 to the minus 10. And what's nice about this, so you can apply the S's small approximation. So we can say this is approximately solubility, let's just be 0.1 squared. So that means we have to divide both sides by 0.1 squared, which is 0.01. That means 1.46 times 10 to the minus 8 is equal to the solubility. So using then, you can use the x is small, s is small. You can use the term as small approximation. And the idea here, you can see it's 0.1 versus this 2s, and 0.1 versus 10 to the minus 8, so that's 10 to the 7. You know, that's bigger by a factor of 10 million. So that's a pretty good approximation, right? So recap with this one. We initial change equilibrium, we start out with 0 calcium, but since there's a common ion, the calcium fluoride and sodium fluoride, there's already fluoride ions there, so you have to include that in initial calculation and then keep it through the equilibrium. Then when we write the terms out, we can use the variable of small approximation, say that 0.1 plus 2 times the solubility is about 0.1, and then solve it that way. Again, if you have a really sweet calculator and you can just go ahead and solve it analytically, just go ahead and do it. If not, you can use the small approximation. So here's one you can try here on yourself, by yourself. What is the solubility of calcium fluoride in quarter molar calcium nitrate? So think about that and let me know what you think, or give it a try. All right, so next thing is the effect of pH on solubility. So is the compound more soluble in acidic solution or neutral solution? So remember the acids, the strong acids: hydrochloric, hydrobromic, hydroiodic, nitric, perchloric, and sulfuric, and the first hydrogen for sulfuric. So hopefully you've memorized all those and understand what it means. And which means that chloride, bromide, iodide, nitrate, and perchlorate do not react with water at all. So there's no reaction whatsoever with water with those anions. So if you look at this, so let's start here. So we're going to determine if it's more soluble in acidic versus neutral solution. So you have barium fluoride. So we have barium fluoride, and this is going to break apart into barium plus 2 fluoride anions. And the question is, does barium plus 2 or F minus react with a hydrogen ion? And the answer for this one is yes. So fluoride is from HF, a weak acid. And remember, weak acids like to form, they like to stay together. And with this in mind, acid will cause the fluoride concentration to go down. So if the fluoride concentration goes down, what happens is, Le Chatelier's principle, we shift right. And that means more will dissolve. So in this case, barium fluoride. So barium fluoride, because one of the ions it produces is the fluoride anion, and the fluoride anion will react with hydrogen to form hydrofluoric acid, decreasing the amount of products, which will cause a shift right, which will cause more to dissolve. So this one is, the answer is yes. More acidic. Barium fluoride is more soluble in an acidic solution. And I'll switch colors for silver iodide. So we have silver iodide in equilibrium with silver plus I minus. And will either of these react with acid? Any reaction? And the answer is no, because iodide is from hydrogen iodide, which is a strong acid. It is a strong acid, therefore it is not going to react with the hydrogen ion. It breaks apart. It doesn't really want anything to do with this. So the answer is no. So you can see here that the only ions that are going to be more soluble in the acidic solutions, they're basically going to be not chloride, bromide, iodide, nitrate, or ClO4 minus. So that's those are the ones don't react with hydrogen. The rest of them do. And then for part C, oh, there's a different color. I'll do pink. Pink for C. So we have calcium hydroxide in equilibrium with calcium plus 2 hydroxides. And will either of these react with acid? And the answer is yes. Hydroxide does. Hydroxide plus hydrogen ion makes water. So because of this, the hydroxide ion concentration will go down, which will cause a shift right, which means that yes, more calcium hydroxide will dissolve an acidic solution than a neutral solution. So it's making sense, hopefully. And sodium triphosphate, or trisodium phosphate, TSP, is this more soluble in acid? The answer is yes. And again, there's a reason. Everything else will. Well, bisulfate, I guess this won't react in acid, but the SO4 minus 2 ion will. So that's a tough one. So this one will react. Well, this one won't. The bisulfate won't, but its product will. Okay, so moving on to other things, precipitation. So we talked about precipitation before. That's a formation of an insoluble compound. So you can use this as a method of separation. So selective precipitation, you can use it to separate out materials. Separations, I had a whole class on this when I was a chemical engineer. It's one of the things we do is we take stuff and we separate out into different components. I mean, there's a couple of ways you can separate things. Distillation is a very common one, for instance. You can do something called liquid extraction. You can do that to rip things out of solution. So a lot of organic chemistry, you can do a caffeine extraction lab to extract caffeine out of something like coffee beans or tea or something like that. So, but one of the ways you can separate metal ions out is by doing selective precipitation. So why would you want to do this? Well, okay. Let's say you're making really pure calcium carbonate. You're trying to sell calcium carbonate to some companies, and your starting material is a mineral called dolomite. Dolomite is calcium magnesium carbonate. So you can take dolomite, you can heat it up, and you can rip off all the carbon dioxide to form calcium hydroxide and magnesium hydroxide. And then this will dissolve in water. You can throw them throw them in the water, and well, or maybe I guess another way is calcium hydroxide. Uh, Maybe better, you could take the dolomite and mix it with hydrochloric acid. So take the dolomite, mix it with hydrochloric acid, make calcium chloride and magnesium chloride. Now you add hydroxide ions to it, and what happens is the magnesium hydroxide will precipitate out first. So you add magnesium hydroxide, you precipitate out all the magnesium ions, and you're left with some really pure calcium hydroxide solution. Then you can bubble carbon dioxide through that, and then you can get really pure calcium carbonate from that. So really pure calcium carbonate they use for things like in paper construction. And the magnesium hydroxide, you can use this as a drug. That's what's in milk of magnesia. So also in Rolaids. So you could take the dolomite mineral starting material, and you can react it, and you can form very high purity magnesium hydroxide. You sell to whoever makes milk of magnesia, and you can take the calcium carbonate and sell to a paper company. So that's the so what in that. Okay, and then moving on, you can also use complex ions to form ligands. So this is how we get gold here in the United States. We find stuff that we will find gold in microscopic quantities, and we take the material, and we kind of make really heavy mud with the gold in it. Then we mix it with cyanide, and the cyanide will dissolve the gold, and then we can take the cyanide and we can just reduce it with other metals to form the gold back out. So, but the idea here, we're making complex ions, and this is called ligand. This is called crystal field theory or ligand field theory, and the idea, you have metals and it gets surrounded by things. So when you have a silver ion in water, typically it ligands to form a silver or two water complex. But more reactive than that is is ammonia. Ammonia will preferentially ligand itself to the silver. And if you see this equation here, we have the silver water complex plus two ammonias forms the silver ammonia complex and two waters. And the formation, the Kf, the constant of the formation constant of this is the products over the reactants raised to their power. Water is a liquid. We do not include water in the equilibrium. You can see the Kf for silver ammonia there is 1.7 times 10 to the 7. So it's huge. That's a huge number. I mean, remember, we're dealing with stuff like with the acids and bases and equilibrium constants. They're so tiny. They're so small numbers. It's like finally we're doing something. We have something that actually progresses so far to the right. We're making things, and ligands are like that. And you can see here the different types of ligands, this formation constants. You have the cyanides. These are huge, right? So silver cyanide, 10 to the 21. So cyanide is a very good ligand there. And you can see these numbers are just gigantic. I mean, absolutely huge. So you can see iron. You see iron cyanide there. I mean, so cyanide binds to iron quite a bit, and that's one of the dangers with cyanide is it binds so strongly to iron. It ruins our hemoglobin's ability to carry oxygen. So let's do an example of this, and I've gone ahead and done some of the homework there. Like, well, not homework. I made it easier. So meaning, so if you look here, you have 200 milliliters of that has 1.5 times 10 minus 1.5 times 10 minus 3 molar copper nitrate in a mixed with a 250 milliliter samples that's 0.2 molar in ammonia. What is after equilibrium? What concentration of copper plus 2 remains? So I've gone ahead and figured out the concentrations there. You don't have to waste the time doing this, writing this out. But the idea, you have 200 milliliters, 250 milliliters, you pour them together to form 450 milliliters, and now you figure out the concentration of everything. So the concentration of copper ions is 6.7 times 10 to the minus 4. And the ammonia concentration is 0.11. Copper concentration initially is 0. And since the Kf is times 10 to the 13, the idea is we're just basically shooting all the way to the right. I mean, it's all the way to the right, and it doesn't really change that much. Or we're going to have a very small amount. So the amount of copper left over is going to be very small. But then what we do is we write the Kf. So I'm still pink. I like blue. So our Kf, this is going to be copper, ammonia, 4 plus 2, so product over the reactants, copper plus 2, and then ammonia to the 4th power. And so we're solving for copper, right? So solving for the copper ion, I can just write it out now. The copper, that's an ugly copper. Copper plus 2 concentration is going to be just the copper ammonia complex all over Kf times NH3 the 4th. I'm just doing the switcheroo here, right? So these terms can just switch algebraically. And put in the numbers, so 6.7 times 10 to the minus 4 all over the Kf, 1.7 times 10 to the 13 times ammonia, 0.11 to the 4th. And put that in our handy dandy calculator, and you get 2.7 times 10 to the minus 13 molar. So that's a really small amount, right? So, well, I guess if you're used to small numbers, there's your small number. But the idea here, it's a little different when you do complexing ions because they form so readily and so effectively that way. So the ice chart, when you do this, you have to think, okay, the ice chart, and you really shift all the way far to the right on this one. So some last things to talk about here with this chapter is amphoteric metal oxide. So metal hydroxide. So metal hydroxides can act like both an acid and a base, and the term for that is amphoteric. And the reason for this is because they do form ligands. So the ligands form with the metal hydroxide, and this is one of the so whats. So for instance, aluminum hydroxide can act like both a base and an acid, depending on the circumstance. And so it's interesting, and it has to do with the ability of it to ligand and to form structures with different materials. So that's it's an application that's explains something, a property of metal hydroxides, the fact that they can be amphoteric based off of the ligand field theory, or we observe that they are amphoteric. And the explanation is with ligand field theory, the ligands form.